Webinars are posted at our website at keypress.com/webinar. You can look at our previous ones. We've been doing these now for over a year. So you can look at our previous webinars and recordings and any documents that go with it. And those are posted. It usually takes me about 2 or 3 days to get those posted up on the website. So look for those around Friday. And also for those of you who are in school districts that accept continuing education hours or PD hours, whatever you call it, we also will email you a certificate of attendance after this webinar. It takes me a day or so to get those out. So those will come to you in a separate email. So just some things to be looking for once the webinar is done. And I have started the recording button, and Andres, looks like we're going to start in about a minute according to my watch. So again, we're kind of just waiting for other folks to join us. Looks like we have about a quarter of the people who signed up, but I do know it's summer. A lot of you are already on summer vacation, and so we know that there'll be some people who have decided that sitting on the beach is more important than the webinar, so that's great. So thank you all for joining us today. And again, those of you just joining us, we are going to keep you on mute. Best way to communicate is through the chat panel on the right-hand side of the screen. Send a message. You can make it private, or you can just send it out to everybody, and you may get some answers from other people in our audience. And we have some people from Croatia, it looks like, and other areas. So we appreciate all of you joining us from different time zones, different countries. It's exciting to see that. So feel free to communicate with each other as well during the webinar. And let's see, Andres, do you want to say something? Let's just check your volume one more time before we get started here.
All right, so this is a final volume check, just making sure that you can hear my voice at the appropriate volume.
It sounds good to me, and I have not seen any messages from anyone at this point, so I'm assuming everyone is hearing us okay. So Andres, I'm looking at the time. I think it's time to get started, so I'm going to turn things over to you. Andres Marty is our presenter for today's webinar, and he is a senior mathematics editor here at Key Curriculum Press. I am Karen Greenhouse, the professional development manager at Key Press. And also online with us is Daniel Scher, who is a senior math scientist at KCP Technologies, and he's going to be helping me answer questions as Andres is presenting. So I'm going to turn it over to Andres. I'm going to mute myself until I'm needed and turn off my screen. Andres, it's all yours.
Okay. Do I need to do something to grab the screen?
All right, we're having muting issues.
My screen is showing yet. Karen, maybe you could let me know.
Yeah, somebody keeps. Okay, hold on a second. I'm trying to make you. No, I'm trying to make you presenter, but did you just? Hold on. Let me make you presenter. So stop. Somebody else is hitting all these things. Yes.
Here, actually.
Andres, make yourself the presenter. There you go. Now you share your screen.
All right.
There we go. A little minor glitch there. Please remember, Andres, you've got the Mac, so your control panel is blocking the view.
Sure. It should be just there in the lower right corner, right?
It is now. It wasn't before.
Okay. All right. Let's get started. My name is Andres Marty. I was a classroom teacher for 13 years. I've been working now at Key Curriculum Press for the last 7 years, and have worked on a number of projects, including a number of Sketchpad-related projects. Worked a lot on Sketchpad 5. And so today we're going to talk about proof in the context of quadrilaterals. But before we get started, I want to do a couple of quick poll questions to kind of get a sense for where you guys are at. So first question. Which version of Sketchpad do you use? If you could quickly just answer one of those. Looks like we got most people already voted. And I'm just going to give it 3 more seconds. So if you have not tallied yet, we'll finish up. All right. Looks good. So it looks like a majority of you are using our newest version, version 5, and then there's a significant number of you that are still using version 4, and that pretty much accounts for most people. I have one other quick poll question I would like to ask. Okay, and here we go. Have you used the Sketchpad Learning Center? So this is a simple yes, no, unless you have no idea what I'm talking about, in which you've got a third choice there. What is the Sketchpad Learning Center? So again, it looks like we got over 90% already, and I will close the poll and share the results.
Andres,
So,
just a couple things.
Yeah.
Your sound seems to get kind of jolty, and I don't know if it's because you're moving your mouse, so just keep that in mind. It kind of fades in and out.
Yeah, let me know if it keeps happening. It happened with you earlier too. I think it might happen when you're dragging something on the screen at the same time as speaking.
Okay.
Okay, well, so about a third of you have used the Sketchpad Learning Center, and another third of you have not, and then the remainder of you don't know what I'm talking about. If you don't have Sketchpad 5, you wouldn't know about the Learning Center, so that would make sense. Let me hide this. Hold on. Okay. So I will tell you about the Learning Center in just a second, but here is the agenda for what I hope to get through today. It's definitely more than we can actually get through in 1 hour, but we will start with an activity called Quadrilateral Pretenders, and I'll explain what that is in a moment. And then we're going to look at the parallelogram properties. We, depending on time, may go into an activity where we construct rhombuses using different properties. And then the last three things here I would like to touch on quickly at the end, with a little bit more time given towards cyclic quadrilaterals. So that's the agenda. But what I'd like to do right now, before we start, this is advertised as a beginning to intermediate webinar, and I'm not planning on spending a lot of time going over really basic things. They'll happen in the context of what I'm doing, but I want to definitely point you all in the direction of the Sketchpad Learning Center. When you're in Sketchpad, if you go to the Help menu, the top thing on the Help menu is the Learning Center. And this is an incredible bundle of resources that come with Sketchpad. And you have lots of video resources, lots of tutorials to get you started if you've never used Sketchpad before and you want to learn how to use Sketchpad, some of the basics. And these 12 tutorials take you from the basics to relatively complex things. And each of these tutorials has embedded movies that you can watch. They're step by step, and you can then do these things and also get video instruction on how to do these things. And so I don't want to spend this 1 hour webinar doing the kind of step-by-step instructing that you could do on your own at the Getting Started tutorials. Another reference, two other references to quickly point you out to, there are Sketchpad tips for everything that you could possibly use in Sketchpad. There is both a video and a one-page comic strip formatted, how does the drag test work, and these things are very student-friendly. And hold on, I just lost my internet window here. There we go. And there's a traditional help system called the Reference Center, and then there are tons of resources for teachers, including sample activities and other things that you can use. All right. So I want to just sort of let you know, if you have questions about how to do things, you can go ahead and ask them, but you can also use those resources that come with Sketchpad 5. Those of you that have Sketchpad 4, you can download Sketchpad 5 for free. It'll time out after 20 minutes. You won't be able to save and print, but you can still access the Sketchpad Learning Center if you want to explore that some more. All right, so the first activity we're going to look at today is this activity called Quadrilateral Pretenders. And so what you see are 4 squares. And the question is, which of these quadrilaterals is always a square? And before I do anything with this sketch, I want to kind of let you know I was in preparation for this webinar. I went through some of our online courses and looked at some of the forum discussions around proof. And a repeated theme that a lot of people have to say is that students often assume that something is the way it is just because it looks like it is the way it is. And that really happens a lot when you look at a static diagram in a book, you make a lot of assumptions about parallel lines, about perpendicular lines, about congruent segments or congruent angles just because of that view of that one particular shape. But in this activity, we're going to, let's see. In this activity, we're going to first drag one point at a time and see what happens. Okay, so if I drag point A, well, that's still a square so far. If I drag point B, oh, well now you can see that even though it happened to be a square in its original position, that simply dragging this point around makes it so that it's no longer a square. So just because it looked like a square doesn't mean in Sketchpad, certainly you can assume it's a square. Okay?
Andres, just be careful. Again, you're fading in and
other
out.
Points do. Okay, and that's because I'm dragging points and speaking at the same time. I will try to do them sequentially, okay?
Okay.
All right. It's hard.
I know it's hard.
So with the blue square, I'm going to go through the same process here, and I'm not going to talk for a second. Already now you can tell it's not a square. In fact, the blue shape is not any special kind of quadrilateral. It's just the general case of a quadrilateral. The orange one. Okay. Well, before I moved point G, I was going to ask people to guess what the orange one was, but I accidentally moved point G, so some of you might actually know too much. So I'm going to come back to it real quick. Let's go to the yellow one. The yellow one, I'm going to drag all 4 points. So you can see that no matter which vertex I drag, I can change the orientation and the size of the yellow quadrilateral, but it always remains a square. So the other questions then become, well, what kind of quadrilaterals are these other ones? I already told you about the blue one. The purple one, you might have noticed this point is, any guesses? Feel free to use the chat panel to quickly throw out your guesses on what the purple quadrilateral is.
Oh, we've got lots of people saying parallelogram.
Right, well, lots of people's parallelogram. And then finally, the orange one. What's the orange one?
Oh, we got John telling us he doesn't know that the yellow is a square.
Okay. All right. Well, some of you are saying rectangle for the orange. Some of you are saying parallelogram. I'm purposely not dragging all 4. Whoops. Talking and dragging at the same time again. I purposely was avoiding G because as soon as I drag point G, you'll see that it is not a rectangle. It is, in fact, a trapezoid. All right. So the question now is, what was the question? How do I know that yellow is a square?
No,
so far I only know yellow is a square. Go ahead.
I said he didn't know that yellow was a square. He still doesn't know.
Yeah. Well, so far it seems to be a square visually. That no matter which points I drag, it remains what appears to be 4 congruent sides and 4 90-degree angles. We can verify that with measurements. Okay, this is not by any means a proof. But I can measure those lengths. I can see that when I change the size, the lengths remain equal. I can also construct the angles and notice that they automatically change to 90-degree angle markers. In Sketchpad, when an angle is 90 degrees, the angle marker will automatically form a square, unlike this one. Oh, man. Sorry. Here we go. Okay. So I'm going to move on. This is really just a lead-in to a series of activities that you can do with students either in the middle school level, where more and more in geometry is being emphasized now in the Common Core, or in the high school level. And you know, the idea where the students go from here, and just for your benefit real quick, I'm just going to show the all hidden. So, you know, it gets pretty overwhelming when you have so many constructions going on in the background. But here in the background, you can kind of see all of how these things were constructed. And you could go one shape at a time. It would be less overwhelming. All right. So now let's move on to one more quick poll question. All right, so for those of you that are from the United States, which is most of you, are you in a state that's adopted the Common Core state standards? We got about 83% of you. I'll give you a few more seconds. It'll be interesting to see what you have to say on this one. All right, we're over 90, so let's close the poll. And so, okay, well over half of you are in Common Core states. A quarter of you are not, so maybe I won't emphasize the Common Core so much. And then, again, another sizable portion of you are from outside the country, so welcome. Okay, let me close this. All right, so what I want to do now is start with a blank sketch and construct a parallelogram. And then we'll start talking about some properties of that parallelogram. And I'm going to use a segment to start. That's one side. And, you know, here's a second side. I'm already halfway done. I mean, every parallelogram, you know, has at least, this, you know, has some kind of one vertex here. And there's nothing special about this angle. It can be any angle. So, you know, and this can be any length, as can this. So half of the parallelogram is really just defined by three free points in the plane. And the whole trick is to get that fourth point. And that fourth point has to be very specifically a point so that it becomes a parallelogram. So in Sketchpad, you can construct parallels and perpendiculars by selecting both an object to be parallel or perpendicular to. In this case, I want to be parallel to this segment and a point for that line to go through. So I want to construct a point, I want to construct a line that goes through this point and is parallel to this segment. So I'm going to construct a parallel line. And you can see now as I bend these points around, if I move them around, sorry, I'll try to remember not to move things and talk at the same time. But as I move things around, this segment and this line remain parallel. I'm going to do the same thing to make the other parallel. I'm going to select this side and this point. And I'm going to go ahead and select the point tool. Notice that when I'm on this line, it highlights. When I'm on this line, it highlights. And when I'm at the intersection, both lines highlight. And now I have constructed a parallelogram. It looks like a little bit more than a parallelogram, and for now I might want to just clean it up a little bit by hiding these lines. And replacing them with segments. Those lines are still there. They still govern the structure of this parallelogram. They are hidden, but they're there. So there's a difference between hiding an object and deleting an object. So, all right, this is a parallelogram, and at this point, if you were doing this with students and you had them construct a parallelogram, one of the great things about using Sketchpad is to have them discover the properties in the first place, which ends up becoming a much more a greater motivator for a proof. If you notice something yourself and then you want to know why, that tends to be more effective than just saying, prove this. It gives some buy-in into the process. So in an activity like this, I would have the kids measure the lengths of the sides. Sketchpad conveniently gave us labels in the process. I would also want to look at the angles. In the Sketchpad 5, you have the angle marker tool. So you can construct the angles, and then you can select those angle markers and measure them. And then I'd have the kids drag the points around and start looking for some patterns, okay? Well, clearly, these two values are always identical, and these two are always identical, no matter which point I drag. And the angles are also paired up. And then there's another relationship that some students might see. You can start noticing, oh, there's a relationship between these two numbers. Well, we can test that with a calculation. So I'm going to go calculate this angle plus the measure of this angle. And notice that that adds up to 180 degrees every time. And so you've got some properties already. There's also generally another series of properties that you can when you look at parallelograms. If you construct a diagonal, you start to get another series of relationships which, let me go ahead and hide these two for now. And you can start looking at some of these angle relationships. Okay. I was going to ask for some input at this point. I have to be honest with all of you. I have never used this format of a webinar before, so this whole ongoing chat thing is a little bit hard for me to follow. But I'm curious at this point, okay, I've shown you sort of a number of properties, and these are the kinds of things that kids would notice. So now you got to go to the next step. How do you, what is it that you're going to do to prove these things? If you want to prove that this is congruent, what are some things that you would, how would you go about it at this point? And I don't know if this is going to work, but I'm asking for people to type in responses into their chat about sort of where you would go from here.
Well, we've already got a comment from Ivana who was talking about how just in the way you were constructing it, she thought it might be better to construct the segments and then hide the parallels. I don't know if you can see her comment.
That's a good point. Yeah. Oh, yeah. Okay. Just to show Ivana's comment, what she's saying is, if I wanted, let me backtrack for a second here. No, I don't want to do that. I don't want to really lose my measurements, but if I do want to show that real quick. If I have So if I construct Ivana's point is that in Sketchpad 5, when you construct a segment over an existing line, the line automatically becomes dashed. And those dashed lines are in fact very helpful in going about the proof eventually anyway. Oftentimes when you see a diagram in a book, though, you will be starting with just a parallelogram and you'll have to add those lines in the first place. So I think
you got a couple of responses. Yeah, there's some responses there.
Okay, so I'm seeing a couple of responses about alternate interior angles. And so that is, in fact, I'm going to go ahead and show the hidden objects and do this the long way. I can go ahead and make these dashed. And then I can also add a couple of more dashed lines. I'm going to actually add this one and this one. And you can see that the fundamental thing that you're going to have to do in order to go anywhere with the parallelogram properties is to use the alternate interior angles that are formed. So in this case, for example, the angle here, the interior angle at B, angle ABC, would be congruent to this angle. Let me color those the same color. Karen, I can hear your keyboard a lot right now.
I know. I'm stopping.
Okay. All right. And I'm not going to go through the whole process of the proof. What I really want to kind of get at more now, it kind of gets to the Common Core idea, and I know a lot of you are in states where you don't necessarily have the Common Core as an adopted set of standards yet. But if you look at the Common Core, there's really quite a large emphasis in geometry on transformational geometry. And if you look at the first set of standards on congruence, it's really about experimenting with transformations in the plane. And the Common Core authors really want this idea of seeing congruence as the ability to take one shape and through a series of transformations superimpose it on another shape. And this is a learning trajectory that should be developed throughout middle school with hands-on experiences, sort of using tracing paper and constructions. But we quickly jump to the side angle side kind of proofs that you need to do right where we were just at, right? I mean, in the end, a lot of the proofs you do in geometry that involve quadrilaterals come down to showing that two triangles are congruent. And so in that spirit, I just want to kind of take another look at this in a different way. I'm going to construct a polygon. I'm going to construct polygon A, B, C. And what happens, if I take this diagonal and construct a midpoint? Mark that as a center, take that triangle, and transform it. Let's rotate it. You can see what it would look like if I rotated 9 degrees. It doesn't help. You could try different degrees. But if you end up rotating it 180 degrees, give it a different color so we can tell them apart. You can see that this triangle is a 180-degree rotation of this triangle around that point. And I'm going to leave it there. I'm going to leave it there just that in my 13 years of teaching, I was always going with the, you got to prove because the lines are parallel, the alternate interior angles are congruent. And then you get the angles congruent. You get this side is shared by both triangles. You eventually get some kind of an angle side angle. Two triangles are congruent. But this sort of, and I don't even know what I'm really, I guess I'm not exactly sure what I'm trying to say. I think that conceptually it's more powerful for a kid to understand that this triangle rotated 180 degrees around this point gives you this triangle. And it kind of makes you see the relationship much more viscerally than just doing a series of proofs, no matter what format you do them in. And yet, this would not have been considered a rigorous proof somehow in my childhood or even in my teaching days in the classroom. I wouldn't have thought to use transformations as a way of doing proofs. So I leave that as an open question. One more last poll question real quick.
Andres?
Yep.
After the poll, there's been some question about the angle marks and how can you mark multiple angles at one vertex, and then the tick marks. So can you kind of show that after you get through the poll? Awesome.
Yeah, well, why don't I do that first?
Okay.
So let's take a slightly less convoluted example, something that's got less stuff going on. Oops. I'm constructing a circle with 2 radii, and therefore I've created a special triangle. Because this triangle will always be isosceles. So there's a number of things, the questions that came up about marking angles. Well, actually, I should have something more complicated so I can show the marking multiple angles at the same vertex. So let's hide the circle. And let's go ahead and add a line here. So with the angle marker, there's a number of ways it works. One way is to simply click on a vertex and drag to the interior, and that will make the angle mark. And so that would work in this case here too. You could drag to this interior, or you could drag to this interior. Now those are 2 separate angles. I'll change the color on this one so you can tell. Okay, so that's just the one method. The other method is that you can click from one straight edge, from one side of the angle to the other side. And notice that when I do this, there's an arrow. Okay, so when you do this, you've actually created an angle that also has direction. And what I mean by that is, if I look at the properties of an angle marker, it can be a simple reflex counterclockwise or clockwise, and it can have a direction. And so right now this is just a simple angle, while if I look at the property of this one, sorry, angle, it has an angle direction. But with these angle directions, you can also then define counterclockwise and clockwise, but I'm not going to get into all that right now. The tick marks, this marker tool, in addition to, so for example, if you wanted the angle that went all the way from here to here, then you could use this method, right? I could use the angle marker. Oops. I guess not. Just a quick other example. So here, if you had, here you have all these different angles, and you want to just show a specific one. So you could start from here and go to this one or to this one. So you can kind of determine which one you're trying to get to by just dragging to that. And then the tick marks. If you click on the side, this is an isosceles triangle, so I might want to show that these two are congruent, and I can do that just by clicking on them. With the marker tool, when you click on a straight edge, any straight object, it'll do this. You can keep clicking to cycle through multiple a series of 4 different markings. You can also use this to do, if you want to show parallel lines or perpendicular lines, you can change the properties of this. You can also use a right click to change it to open arrow and so forth. All right, so those are, the marker tool really does a lot of things. It does the angle markers, it does the hash marks, and it actually just draws in space, which ends up creating an image that you can transform or do other things with. So that's the marker tool. All right, real quick, the poll question here. So I'm curious as to the role of proof is really different at different eras and different regions. So I'm kind of curious how many of you really don't teach proof at all versus sort of a pretty informal level of proof? You want your kids to justify things and explain things versus some more formal type proof, flow charts or two-column or actual paragraph proofs that are sort of more the style that are used by mathematicians. So got about 80%. Get a couple more votes would be great. Curious to see what the spread is here. All right, we're at 86%. I'm going to stop it in a couple seconds. Okay. All right, so about 10, yeah, interesting spread here. I think I'll just let this stand on its own comment. I think the two-column proof, which was certainly the standard when I went to school, still seems to be the standard in about half the contexts. I know that looking at some of the discussions in the online courses around proof, another common trend is that kids are separated, and the ones that go into sort of honors tracks get proofs, and the ones that are in the more applied tracks do not. Anyway, I was actually curious as to what you all do. I think I'll close this and close this. And just wanted to go back for a second to the Common Core just to make mention, since I brought this up in the first place, about the transformational approach. So the congruence is all done in terms of rigid transformations, and then the, whoops, sorry about that. And then the similarity is done in terms of dilations. And then the things that we were just talking about, though, the properties of the parallelogram, are part of this part here, proved geometric theorems and proved theorems. So it's interesting that the Common Core has really singled out parallelograms as something that students should really understand, more so than all the other types of quadrilaterals, which has been pretty common in my experience of teaching geometry. You talk about rhombuses and trapezoids and rectangles and squares and everything, but here they really kind of focus on triangles, and then they focus on parallelograms, including the ones that we were just talking about. The opposite sides are congruent, opposite angles congruent, diagonals bisect each other. However, one of the most interesting activities that I've done, and it does involve rhombuses, and I'm going to try to do this one right now again. I'm going to invite you to all participate in this process using the chat window. I love the comment about why only focus on just one type. I'm totally with you on that. I think, exactly. A multitude of approaches is great. But using the chat box, I would like to hear some ideas of how we could construct a rhombus. And I want to, the purpose of this activity is really not to find the way to construct a rhombus, but there are many ways to construct a rhombus. So I would like, I don't know how well this can work with the chat, but perpendicular bisector of a segment. Well, that's the first one up. All right, so let's do that. Here's a segment. Perpendicular bisector. All right, so to construct the perpendicular bisector, I need a midpoint, and then we'll construct the perpendicular bisector, or the perpendicular, I should say. And then assuming that from this point, so this is to Frederick. So I've got the perpendicular bisector of a segment. Then what? This is going to be hard because we've got all these different ideas coming in at the same time, and it's hard to know whose are whose. Okay. All right.
But I mean, it's neat to get everybody's feedback.
From here,
I'd just pick a couple on.
Yeah,
I would
great.
just pick one. Just pick one. It's great.
Now well, I actually have a question, which is, where does the other point go here? What do I do now? Well, I'm going to have to make some assumptions here, but I'm going to put a point here, and then I'm going to, Kendra's telling me to listen to Ruth. See, I can't see them all at the same time. Put a point on the bisector and reflect it. All right, thank you. I put a point on the bisector. Okay, how do I reflect it? Well, I need to make this into a mirror. So I'm going to mark that as a mirror, and then I'm going to reflect back. Ah, there we go. And so now I can construct a
And
rhombus.
Andres is using the polygon tool. For those of you with Sketchpad 4, that's not an available tool.
Yeah, in Sketchpad 4, you would just select the 4 points in order and then go to construct polygon interior. But Sketchpad 5 is definitely more user-friendly. All right, so this is a rhombus, and it was built based on certain properties, but I want to try another approach. And let's see. I'm sorry. This will be two radius. I see two radius of a circle and then parallels. All right, let's try that. Two radius of the circles. Maybe while I'm doing this, Karen, you can look at the other suggestions and let me know of a third technique to follow. Just I can't do both at the same time. But
and can you minimize your control panel? It's blocking your screen.
Thank you. So we have this, all right, because the two radii of a circle ensure that these are going to be two congruent sides, and then I believe the rest of it was to make a parallelogram out of it, which is certainly one way we can go from here. Just like we did a minute ago, parallel line, whoops, I meant to make it parallel to this. And then do the same thing over here. But just for the fun of it, let's not finish it that way. What's another thing I could do at this point? And maybe the original suggestion was actually different. I can't.
Oh, your control panel came back on.
I know, I had to move it because I'm trying to read the comments.
Oh, okay.
That's
Well,
okay, so rhombus must be so the argument here is a rhombus must be a parallelogram, so you finish up the parallelogram, and I don't know, make a triangle and reflect it along the non-radii edge, which is the one I was getting at. This one, again, involves, another way to do it is involving reflection. Mark this as a mirror, and then reflect those two sides. Okay? So this is another way. Karen, is there like a third approach that would be different that somebody else suggested?
I'd have to go back. I think people get the idea, only because I'm looking at our time, Andres. You have about 20 minutes left, and
Sure.
I know you had so much to do. So I think they got the idea here, and we had some great discussion about a rhombus and a kite. So going on.
Okay, good. So the thing that in the end, okay, we'll just stick with these two, or I'll do one more just for variety, which is all right, so starts off similar to the last one. Whoops, I didn't want to construct that point. And then we could use yet a third circle to get like another point. Okay? Anyway, the point I really want to make is if I take all of these rhombi, oops, and I hide all of the objects that were used in constructing, this makes for a pretty interesting challenge in and of itself for students, is to look at these objects and try to figure out how they were constructed. You know, which properties were used, because they all behave slightly differently. You know, this is kind of hard to see sometimes, but this one has there's certain behaviors this one has which are really distinctive and different from the behaviors that this one has. And different from this one. So it's actually really, you know, in fact, this one might not even be constructed right now. There it is. It is a rhombus. And so just a thought, you know, just taking these original objects, and then, you know, you can always show the hidden, but to really just look at their behaviors and think about how they were constructed based on how they are dynamically when you drag the points. All right, so I'm going to jump ahead. Yeah, we have a little less than 20 minutes. Another series of standards in the Common Core center around polygons described in the circles section. So here, this one here, construct the inscribed and circumscribed circles of a triangle, improve the properties of angles for a quadrilateral inscribed in a circle. So I wanted to look at that one for a second. There's a circle. There's a quadrilateral, but I'm going to redo that because I actually want to do it, instead of just having the quadrilateral without edges, I want to make it with edges. So I'm going to pick the polygon tool with the segments. And now when I construct it, I will get a cyclic quadrilateral. So this is constructed so that, you know, all of 4 points, all 4 vertices of this quadrilateral are on the edge of the circle. We get a cross quadrilateral if we go beyond the point, but I'm going to just quickly mark the 4 angles and measure them. So again, you can see how this would be a pretty easy activity to give to kids and have them explore it in the first place. You don't even tell them anything. Just construct a cyclic quadrilateral, and what do you notice? So, you know, things are not so obvious at first. But one thing that's really fascinating is if you take a look at this angle right now, ABC, it's 78.36 degrees. So if you just look at that, it doesn't really tell you much. But what's really interesting is when you drag point B. And what's interesting is that when you drag point B, notice what changes and what doesn't change. Well, the angle in question is angle ABC, and yet when I drag it, it doesn't change. It stays exactly the same size. And yet these 2 angles are changing. And you can maybe then say, you know, certain values will be more obvious than others, like how about that, 107 and 73. And you can start to see how you could take the sum of this angle and its opposite, and you find that the sum is 180 degrees no matter where I drag this point. The same thing happens here on the other side. No matter where I drag this point, which is CDA, it remains the same size, 101.64. And these 2 angles are adjusting, but their sum remains 180. So that's one of the set of properties of cyclic quadrilateral. This has everything to do with inscribed angles. And thanks for reminding me. Try not to drag and talk at the same time. This has everything to do with arc angle. So if I'm going to measure this angle, or this arc I should say. So this arc, ABC, is 203. Let's change it so it's something a little different. Let's make it a sort of a nicer number. How about like, I can't get it to be exactly something, but I'll go down to like 195.6. And then if you look at, that's, you know, and I should have actually made this. Maybe I should construct this. Let me construct it so you can actually see it. Oops. All right, so we can see this arc now, ABC, and it has 195 degrees, and then angle ABC, you'll see is 82.2. So you can start to see this relationship of the angle being half the measure of the arc it's inscribed in. The other thing that's really fascinating about cyclic quadrilaterals is what happens when you construct a perpendicular bisector. So if I construct a midpoint and then construct a perpendicular, it appears like this goes straight through the center. And that's true for any of the sides. And it looks like all of the sides of the cyclic quadrilateral, their perpendicular bisectors, go through the center. Right, this gets back to simply the relationship between a chord and its perpendicular bisector, right? So if you have any chord in a triangle, and you construct the midpoint and then the perpendicular, whoops, it's the relationship that the perpendicular bisector of any chord of the circle goes through the center. But that proof, too, is also really kind of interesting. I'm not going to get into it, but I conceptually was having a little bit of a tough time. Here in this construction, that center is given because you've created the circle. But, how do you really prove that this thing goes through the center? I mean, really what you have to do is do something more along the lines of, I believe, of some kind of an informal argument where you have to say, okay, I can prove that these two triangles are congruent, right? I can prove these two triangles are congruent by side angle side. I know this is the perpendicular bisector, so let me construct the actual separate segments and mark them. Oops, I don't want it to be that. So I can show those are the same. I know that these are 90-degree angles, and I see that they have a shared side. So by side angle side, I can prove that, and that's really this theorem that any point on the perpendicular bisector is equidistant from both endpoints. And then you just have to assume, I'm assuming the logic here is that you can then make the case that at some point, this point has to be at a place so that these two lengths are the length of the radius of the circle, and therefore that must be the center. I'll leave my fuzzy logic exposed at that point and see if you have comments on that. And quickly jump to two other topics that are also, I think, really interesting. One of the most basic constructions you can ever make, and yet leads to one of a pretty challenging proof. I'm just constructing, in fact, I'm just constructing a generic quadrilateral. This time I just used it using the segment tool, so you could do this in any version of Sketchpad. All right, nothing special about this. It's a general case of a quadrilateral. But I can take all four sides and construct midpoints on all four of those sides. And then I can construct the quadrilateral between those midpoints. And the question is, what shape does that form? Feel free to use the chat panel.
We're getting lots of answers. Parallelogram seems to be the consensus.
The main answer, and it is a parallelogram. Now, how can you, with measurements, show empirically that's a parallelogram? Well, you can actually measure slopes. So I can take these two segments, for example, and measure their slopes. Sketchpad superimposes everything onto a coordinate system. I don't really need to see the coordinate system right now. Go ahead and hide the grid. And so you can see these two have the same slope. I can do the same with the other two. Okay, so you can see the slopes, they do in fact to always be identical. And so that is the midpoint quadrilateral theorem, and proving that this is always a parallelogram. I will leave it as an exercise to the viewer. It's not easy. Last thing I want to show, and then I'll take questions. This is true not just for quadrilaterals, it's really true for any polygon, but since the theme has been quadrilaterals, I'll stick with that. And and then you can look at, is the interior angle sum of quadrilaterals and so forth, and the exterior. So I'm going to actually just go ahead and do the exterior angle here for a second. Oops. And so you have these 4 exterior angles. I see that the last one I constructed was a little suspect. Okay. And now I'm going to construct the exterior angles. And I don't like that they're, let's change this color here. And then, whoops, how did this become pink? Measure those 4 exterior angles. And since it's 5 minutes till the end, I'm just going to jump to the calculation. And this is not so obvious right away, but if you do add all 4 of these together, you get 360 degrees. And that's true no matter how you manipulate the angles. Now, one thing that's really cool to do in Sketchpad with this situation is that you can also, something I rarely use, but this is one of those instances where rather than using the translate arrow tool, which is sort of the normal way we think, there's also a rotate and a dilate arrow tool. So with the dilate arrow tool, I'm going to take one of these sides and I'm just going to select everything and converge onto that one point. Now watch what's happening as everything dilates to point A. Okay? I'm going to go slow. So the shape is just, back to my point earlier about how congruence is rigid transformations and similarity is dilations. You can see what's going on here. Again, I'm sure I'm making lots of slurred noises. I'll stop moving things for a second and talk. But I want you to pay attention to how it's a similar figure, but then what happens at the end. Oops. Select everything. So when you get to the end, the polygon has disappeared altogether, but the 4 exterior angles are still there, forming one full circle. So it gives some explanation of why the sum is 360 degrees.
I love that one. And actually, when I used to do that, I actually did that first, so they came up with the idea of what was happening, and then you actually have them do the calculation. Just
Okay, sorry I've been not being able to do a good job of reading what people have been saying as I've been going on. So Karen, are there any questions or themes that came up that I should address?
No, everyone's just been commenting on it. So no, I haven't seen any additional questions. So anyone who has a question, if you want to ask it now would be the time. So if you have a question, but I haven't seen any that have come up. Just people have been kind of commenting on. We've got some, wow, oh my God, that's amazing. So if you have any actual questions, you want Andres to show something, that type of thing, that'd be great. This would be the time. Send them in the control panel.
So, well, I appreciate the positive feedback you guys are giving me. I actually feel like I didn't really address the actual doing proofs that much. My bigger point I was trying to make is that I think that proofs are just inherently more interesting to do if you first discovered the relationship yourself. Then it's like, okay, well, why is that? Otherwise, it's just an abstract problem that you have no buy-in to. Plus, when you use Sketchpad, you know this idea that comes up in the Common Core about looking for repeated reasoning and structure. You can see that as you're dragging points around, you start to see certain patterns, structures, geometric relationships emerge visually, which is a great sort of first step towards thinking about how you would then do, you know, what properties are at play that allow you to develop a proof. So that was hopefully what I got
There's
across.
no questions. I'm not seeing any questions, Andre. So you must have answered all of them. It's amazing.
All right. Well, thank you all for joining us today, joining me and Karen and Daniel. And Daniel, thanks for answering all those questions. And we hope to see you again. And
just a reminder that this webinar will be posted probably by Friday up on our archived site, keypress.com/webinars. And we do have some webinars coming up in July and in August. So look on the same website, keypress.com webinars, to check out the ones that are coming up. And if that's it, I still don't see any questions, so I guess we'll just end the webinar. Thank you, Andre, very much. Oh, wait.
I'll end on a quote. This is a quote from one of the participants in our current online course, which I also meant to share if you guys are interested. Our online courses are really a great place to have these kind of discussions. But this quote was about thinking about using Sketchpad and proof. Students can begin to understand why a relationship is true and gain confidence in their thinking because they have the ability to test their results. And I think that's a key idea there, is this sort of the confidence idea and the ability to explore, get feedback, and have that motivate rather than dismotivate or throw barriers in front of students, which is often what happens when they're trying to deal with proofs. So anyway, thanks again. Have a good evening.
Thank you.